So we'll continue on. This is at the bottom of the second page of your notes. And this is just some information about differentiability and continuity. I'm going to give you an alternative form of the derivative, and we'll talk in the next example about where you would use this form. So the derivative of f at a c value, remember c is a particular x, could be known as f prime of c. So in other words, you would have a number in place of just an x, and that would be the limit as x approaches c. So no longer in this definition are we using delta x and 0. It'll be the limit as x approaches c of f of x minus f of c over x minus c. And in our next video, we'll be using that definition when we just know an x value. But that leads us to talking about what does happen at a particular x value if f is differentiable. So in other words, if this limit exists at x equals c, then we know that f is continuous at x equals c. And so before moving on with that, I want you to consider whether or not the converse of that statement would be true. And actually, that is not true. So down at the bottom of your page there, I have this statement about f is continuous at x equals c if you know that it's differentiable. Is that converse true? No. Continuity does not imply differentiability. And I've drawn for you a graph. I think you should copy this down at the bottom of your page. And this is an illustration of a graph that is continuous, but this limit at, in this case, x equals 0 would not exist because this is a definition of slope. And for this graph, you've got a slope here of +1. You've got, or a positive value at least, you've got a slope of this side of negative. And so from the left and the right, the slopes are different. This limit would not exist. And this happens anytime that you have a graph that has a sharp turn. So an absolute value graph would be one that this happens on, and some other graphs that you may encounter. Anytime they have a sharp turn, a point, as opposed to a curve. If you have a parabola that's got a curve, we can look at the slope of the tangent line for a parabola. In fact, the slope of that's going to be for a horizontal line, which would have a slope of 0. But the tangent line to this graph is actually vertical, and vertical lines have an undefined slope. And so that happens anytime you have a sharp turn. So this would be not differentiable at that sharp turn. So I'm going to have us continue on and look at your example that is at the top of your notes on the next page. And I'm going to erase this for us and get things set up, but go ahead and stay in this video. So this is at the top of your next page, and you're asked to find the derivative at x equals c for f of x, which equals x to the third plus 2x, and you're given a c value of 1. So notice that you're really given even less information than an ordered pair. All that you have is the x value of 1. So we'll use that alternative definition of a derivative. So remember that a derivative is the slope, and we're doing f prime of c. I'm going to go ahead and rewrite that formula for us since we just got it. So that would be the limit as x approaches c of f of x minus f of c all over x minus c. So your slope would equal, in this problem, the limit as x approaches. All right, now our c value is a 1, and we'll do f of x. Well, f of x is this function, x to the third plus 2x minus, and then it says to do f of c. So we're to do f of 1. So I'm going to write that up here, but I'm actually going to do f of 1. So f of 1 means we're going to plug in 1 everywhere that there's an x in our function. So that would be minus, I'm going to use parentheses, 1 to the third plus 2 times 1. And then in our denominator, we have x minus our c value, which is 1. So once again, I would encourage you to try direct substitution. If we plug in 1, we'll have 1 to the third plus, so that'd be 1 plus, and then 2 times 1, that's 2. So 1 plus 2, this will be minus 1 and minus 2. We end up with 0 in the numerator and 0 in the denominator, and we have that indeterminate form. So we're going to have to do some work. So we'll have the limit as x approaches 1 of x to the third plus 2x. And then if we simplify this, we have 1 plus 2. So that would be 3. And so we'll have minus 3. And then your denominator is x minus 1. All right, now we have a polynomial, but it does not factor. So a few of you ran into this in your homework previously where something didn't factor, but you knew that you had to do some work with it. And the work that we're going to have to do is we're going to have to try some synthetic division. So what you do is you look at factors of this last number. And so fortunately, it's 3, and 3 doesn't have very many factors. You have a factor of 3 and you have a factor of 1. You would have to try your synthetic division and look for a remainder of 0. In order to save us some time and me some space, I'm going to tell you that the factor that works is a 1, but I'm going to show you that work. So I'm just going to do that right here. 1 is my divisor, and I'll use my coefficients. So x to the third is a 1. For 1 x to the third, I don't have an x squared. I need a 0. I have an x, that's a 2, and then a constant negative 3. And so synthetic division begins with a bring down of 1. We multiply 1 times 1, put it here, and then we add. So that'd be 1, and then 1 times 1 again is 1. We add, we get 3. 1 times 3 is 3. And this one is the one that worked. I got a remainder of 0. So what we have found here is that x to the third plus 2x minus 3 will factor. In this case, we want the factors of this polynomial expression. One of the factors is going to be x minus 1. I guess I'll put that down here. So this will be the limit as x approaches 1 of x minus 1. And again, I got that 1 by thinking about what are my factors of 3. And I went ahead and told you that 1 was going to be the one that worked. And then this factor, which is 1 degree less than what our original problem was. So this was an x to the third. This is going to be the coefficient of x squared. So 1x squared plus 1x plus 3. So those are our factors of this expression. and then it's over x minus 1. Now, there was another clue that 1 was going to be the one that worked because I wanted this x minus 1 to cancel, and that's what happened. And now you can do your direct substitution. So your slope is going to equal, I'm going to plug in 1, so 1 squared plus 1 plus 3, and that's going to give me a slope of 5. So I found the slope of the tangent line at the x value of 1, and that slope turned out to be 5. So that would also be known as f prime of 1 in this problem. So you could either say your slope is 5, or sometimes it's nice just to know that that's the derivative at the x value of 1. So f prime of 1 is equal to 5. And that'll be the conclusion for this video. We'll have one to go.